This is a video on balancing chemical equations, and I've dedicated this video for a student of mine who's still finding it a bit fuzzy. Not a problem, so I decided to make another video on this and to approach it from approach it through a different lens, and hopefully they can understand it at the end of the day. So I hope this helps. I'm going to start from the very beginning with what an equation is in general. So equations, they're basically symbolic representations of the physical world. Okay, be it a mathematical equation describing how gravity works, or a chemical equation describing how a chemical reaction takes place. Now I'm going to focus on chemical reactions. So a chemical reaction is when you've got two reactants. Let's call this reactant 1, could be anything, and reactant 2. Okay, these two are let's call it raw material. I want you to think of like a factory that takes some raw material, and this means here to make. They make some product. Okay, let's call this, I don't know, a slab of material. So I'll let you use your imagination for this. Some slab of material. So something plus something gives you something else. Okay, that's an equation that's describing. So I've written down on this paper, on this device, in this case, something that's happening physically in the world. Okay, this is a symbolic representation. I've used symbols here. I've used letters to describe what's happening in front of me. That's what science is about. Okay, you formulate an expression to describe what's happening around you. Now, in chemical equations, there's a rule you can't break. It's one of the basic laws of the universe. It's known as the law of conservation of mass. This was discovered in the 1700s by a French chemist named Antoine Lavoisier. And it basically tells you that you cannot create or destroy atoms. You can only rearrange them in a chemical reaction. Here's an analogy. Suppose I give you some blue Lego and some red Lego, and then you decide to make in front of me, over a certain amount of time, a blue and Lego castle. The law of conservation of mass tells us in this analogy that you can't have black Lego appearing out of nowhere here at the castle, or you can't have green Lego or white Lego. Okay, whatever you start with, you end with. Okay, that's what an equation is all about. It's all about balance. I love using this analogy with students. They understand it quite well. Equations are seesaws, okay, pictorially. Whatever you have on the left, you must end up on the right. Okay, both sides have to be equal, in other words. Blue Lego on the left, let's say you've got, I don't know, 100 blue Lego on the left. You've got to have 100 somehow on the right. And suppose you've got 100 red Lego on the left, you must have 100 red Lego on the right. Okay, 100 on the left, 100 on the right for the blue and red Lego. That's an analogy there that I like to use. And chemical equations, just like any other equation encountered in like maths, they're all about balance. Balance is the key word. You must have an equal number of the same type of element on both sides of the equation. So here's a seesaw. Let's call this element X. Let me draw it here. Okay, here's the seesaw. I've got element X, that could be anything. It could be gold, for example, on the left. And I've got element Y on the left. On the right, element X, element Y. Okay, whatever I begin with, okay, two elements, I must end up with these two elements. They could be in a different form. They could be mixed together. They could be separated in some way. But essentially, whatever I have on the left, I must have on the right. LHS, left-hand side, must always equal the right-hand side, RHS. Okay, it's all about balance. Let's do a very simple example. Let's suppose I want you to think of, in terms of the physical world for now, not equations. Suppose I've got me on the left, weighing 80 kilos, and I ask you, how do you make the seesaw balanced? Okay, because at the moment it's tipping over to the left. To make it balanced, it's quite simple. I'm hoping you would say you would have to have someone weighing around 80 kilos as well on the right for it to be balanced. Okay, there's no surprises there. There's no magic here. It's intuition. Okay, it's logic. That's what the middle bit is all about here. Equals, right? So I'm on the left-hand side, LHS, and someone else is on the right-hand side, RHS. Let's do some more examples. Suppose I've got a scale. On the left, I've got a basket. On the right, I've got a basket. On the left, I've got 2 apples in that basket. Suppose I now tell you, how would I get this scale balanced? How would I make it balanced? Well, you would say, hopefully, you would have 2 apples on the right as well. Let's do another one. Suppose I've got a seesaw and I plonk 3 smiley faces on the right-hand side of the seesaw. How many would I need on the left-hand side? I'm sure you would tell me 3, right? It's the same principle. Let's now let's take it up a notch and introduce numbers and letters. Suppose I've got a seesaw like this. Let's use some basic algebra. 2 is equal to star plus 1. What's the star? Well, we know the left-hand side has to be 2. The right-hand side has to be 2 as well. The star plus 1 is 2. The star would have to be 1. Let's do another one. Suppose I give you 10 minus y on the left-hand side and 5 on the right-hand side. 10 minus something gives you 5. What is that something? The y would have to be 5, right? Let's keep going. Let's do another one. Suppose I've got z on the left-hand side is equal to 20 plus 20 on the right-hand side. 20 plus 20 is 40. The right-hand side is 40, so therefore z, the left-hand side, has to be 40. Let me ask you a trick one. One last one. 0 is equal to a plus 0. What's a? So something plus 0 is 0. I'm sure you would say 0. That's the idea. So now let's get into chemical equations. Let me start off with a very classic textbook example, and that involves the production of water, H2O. So suppose in an exam they give you this, H2 plus O2 makes H2O. Okay, now this may look a bit scary. Let's break it down. Now, I'm a firm believer in the idea of following this algorithmic process, this step-by-step process. Okay, everything to me is sort of like a recipe when it comes to solving equations. It's a simple recipe. Now, the rules of the game are this. Here are the rules of the game. I'll do it here at the bottom. Here are the rules. There's not many. Rule number 1. You cannot add numbers, in this case subscripts, so numbers that go at the bottom, to elements. For example, H2, suppose I wanted to add 2 more hydrogen atoms. Okay, so here H2 means you've got 2 hydrogen atoms stuck together. That's what the subscript 2 means. I can't all of a sudden go in the equation, rewrite it as this, because I'm basically creating atoms in this case. Okay, I'm going from this to this, which is impossible. According to this law here, the law of conservation of mass, you cannot create or destroy atoms. Okay, you can only rearrange them. So this is wrong. Can't do that. Massive X for that. Number 2, you can only multiply number of atoms by some number. Okay, typically an even number, not necessarily, could be 1, could be odd as well. So for example, suppose I've got 2 hydrogen atoms. Okay, I can only multiply, let's say by number 2 to give me 4 hydrogen atoms. Okay, in this case, what I've done is I've basically added more hydrogen atoms. I haven't created them, I've just added. Number 3, you can only, so number 2 leads into number 3. You can only place numbers. Okay, in maths and in chemistry, these are called coefficients. Coefficients, okay, numbers, I should say, at the front. So when you place a number at the front of a symbol or letter, that's called a coefficient. Only place them at the front. For example, suppose I've got H2 in the equation. I can only put the 2 here. Okay, I can't put a 2. I can't put a 4 down here. Replace that with a 2, with a 4, or anything else. Okay. So numbers only go at the front in chemical reactions. So they're the 3 rules. And also, if you have, it's not really a rule, but if you have, let's say, actually, I'll do an example with that. I won't do it here. Write it here. So these are the 3 rules. You can't add numbers to subscripts. You can only multiply the number of atoms by some other number, like this. And you can only place numbers at the front, at the start of elements. These are the 3 rules. So let's see how these 3 rules work. Let's try and see what's happening here. So we need to work out if this thing's balanced or not. The very first step, I'm going to use a different color, and I encourage all students to use this recipe, these steps in an exam. Okay, no matter how good you are at these, put your ego to one side and just use steps, because in an exam you're under pressure, you've got time restraints, and you can make mistakes quite easily. So it doesn't matter how smart you are, always follow this recipe. Step number 1, I'm going to use blue here, is to make a list from left to right. What does that mean? Well, let's separate the equation first, where that arrow is. The arrow basically means to rearrange. Remember, by definition, you can only rearrange atoms. You can't create or destroy them, according to the law of conservation of mass. And to make a list from left to right means, so let's start from the left, H, and then O. Now, the beauty of this process is that on the right, it's the same thing, H and O, because you can't make or destroy atoms. Whatever you have on the left, you have to have it on the right. So always have them in the same order, H at the start and then O second, okay, because it helps to keep track of things. Number 2, count. Count the number of atoms. We're only counting atoms here, not molecules. Atoms, okay? The building blocks of matter. Here's what you do. You put an arrow and you say, in this case, there's 2 hydrogen, right? So put a 2. Oxygen, there's 2. On the right, there's 2 hydrogen. And on the right, there's 1, okay? 2 hydrogen and there's 1 here. There should be 1. The chemists leave this out. Put in, just leave it as the O, as it is. So far, so good. And then step 3 is to see which element or elements aren't balanced. Okay, use a different color for this. I'll use purple. Now the H on the left and on the right, okay, so we're starting from top to bottom, working our way down. They're balanced, so tick. So far, so good. Now the oxygen, we've got an issue. There's 2 on the left, 1 on the right. The seesaw's not balanced. So what do we need to do? Now the rules of the game are, if you recall, you can only multiply, right? To turn that 1 into a 2, we can only multiply, we can't add. So we multiply by 2. The only thing we can do is multiply by 2 to get 2. And there we have it. They're balanced. So the 2 in this case, remember the rules, you can only place numbers at the front, the coefficient, right? It's the thing that you multiply by, this 2 that goes at the front. So this, because this is a compound, H2O, the H and the O, they're glued together. They're not separate. Helps put brackets. That 2 goes at the front. Okay, so everything's balanced. However, the hydrogen now, there's now 4 of them. There's 2 lots of H2s, which is 4. Cross that out and put a 4. Now the left-hand side's in trouble because there's 4 hydrogens on the right and only 2 on the left. So how do we turn this 2 on the left into 4? We can only multiply by 2, right, to get 4. Remember, you take the thing that's being multiplied by and you put it at the front, the coefficient. You can only put it at the front. Now there's 2 lots of hydrogen, 2 lots of 2, which is 4. So 4 on the left, 4 on the right, 2 oxygen on the left, 2 oxygen on the right, and that's it. That's how you balance an equation. I'm going to do some more equations. I'll do a simpler one now. Let's go back to blue. Let's do another classic. Lithium plus fluorine gives you lithium fluoride. Back to the recipe, step 1. Okay, let's separate this thing. Step 1 is to count. Okay, so, or before that I should say, is to make a list. So from left to right, make a list, lithium first, then fluorine, and the same thing on the right. Then we count. Step 2 is to count. I'm going to use a different color for this, just to make it easier for you to see what's happening. Let's use red. Number 2 is to count. Lithium, there's 1. Fluorine, there's 2. Right? On the right, lithium, there's 1. Fluorine, there's 2. Oh, sorry, there's lithium, fluorine, there's 1. Then we check to see what's not balanced. Okay, number 3. Let's use orange. Lithiums are balanced, no problem. The fluorines aren't. On the left, there's 2. On the right, there's 1. How do we turn this 1 on the right into 2? We can only multiply. So we times by 2 to get 2. This 2 that's being multiplied goes at the front. This is a compound, if you recall. Whenever you see 2 or more elements stuck together, that's a compound. That's one big thing. All good. However, there's now 2 lithium. 2 times Li means there's 2 lithium. So that becomes lithium. It becomes 2. How do we turn the lithium on the left, which is now in trouble, into 2? We multiply that by 2 to get 2. Put that 2 at the front. And that's it. We've balanced it. Let's do another one. This is one of my favorite examples, and they have asked this in the past in exams. I'll tell you why I like it so much. I'm sure students will like this really much. Suppose I give you this. This is the reaction of an acid and base, hydrochloric acid plus sodium hydroxide, a base, to give you water, H2O, and a salt, table salt in this case, sodium chloride. Don't worry about what they are for now. Let's follow this process once again. So let's separate this equation. It may look like a lot, but don't worry, it's the same idea. Step 1, let's make a list from left to right. First element we see is H, hydrogen. Okay, so using a periodic table to identify. Cl is the next one, Na is the next one, sodium, O is the next one, and we stop here because H, we've already written it down. That's the hydrogen. Same thing on the right hand side, just rewrite it. Step 2, let's count. Okay, it's a counting game. Hydrogen, we can see there's 2, 1, 2. Chlorine, there's 1. Sodium, there's 1, and oxygen, there is 1. That's the left-hand side. Right-hand side. Hydrogen, there's 2. Chlorine, there's 1. Sodium, there's 1. And oxygen, there's 1. What do you notice here? Tick, tick. The hydrogens are balanced. Chlorines are balanced. Tick, tick. Sodiums are balanced. Tick, tick. Oxygen is balanced. Tick, tick. Equation's already balanced. Okay, this is a trick question, and I hope they ask you this in an exam because it's very simple. So that's the idea. That's how you balance equations. You go left. You basically work your way through the recipe. I'm going to do one more just because these types of questions pop up often as well. This is the production of ammonia. Ammonia is used in household bleach. So nitrogen plus hydrogen gives you ammonia, NH3. Let's do this one. Step 1 on the side. Let's separate this and let's make a list left to right. There's nitrogen, N, and there's hydrogen, H. Same thing on the right. Step 2, let's count. Nitrogen, there's 2 on the left, and hydrogen, there's 2 on the left. On the right, there's 1 nitrogen, and on the right, there's 3 hydrogen. Okay. Oops. Okay, nitrogens, we have an issue. On the right, it's not balanced. Let's turn this 1 into a 2 by multiplying by 2 to give 2. That 2 goes at the front. Right. And there's now 6 hydrogen. Because 2 times H3 means there's 2 lots of 3, which is 6. Okay. H3 looks like that. Okay, that's H3, and there's 2 lots of them, so there's 6 atoms in total. So 3 now becomes 6. Nitrogens are fine. Now the hydrogens aren't, okay? 2 and 6. Now, how do we turn the 2 into a 6? Common factor with 2 and 3 is 6, right? So it's 3. 2 times 3 is 6. It's the only way to get 6. And that 3 goes at the front of the hydrogen. So now you have 6 hydrogen, and now they're balanced. Okay, and that's how you balance chemical equations. I encourage you to do examples, as many as you can, the ones I gave you in class on worksheets. If it still doesn't make sense, try and ask a peer in class, a mate, and hopefully they'll be able to talk you through their way of looking at it. But that's how you do it. That's the simple recipe.